So we'll finish that off today, and then we'll start on basically mechanisms, classifications of reactions, and that sort of fun stuff. So before we start this, let's do a little review of what we did last class. So remember, one of the things we did was that we used the Kahn-Ingold-Prelog rules to rank substituents. And we did this because we wanted to assign a configuration at a carbon that was chiral or asymmetric. And so to be able to do that, you need to be able to rank the various substituents. Periodic table here. Mm, 15 more seconds. Okay, let's see what we have here. Okay, so B would be first, that's consensus. D would be second. And then A and C, third and fourth. Okay, so remember with the Kahn-Ingold, with this ranking substituents, the first one is atomic number. So chlorine's atomic number is 17. Nitrogen is 7. Carbon is 6. So what's going on here? So chlorine should be first, and then the amine would be second. And that leaves A and C to be the next, would be third and fourth. And so they each have carbon, and then we check the atoms that the carbon's bonded to. So this is bonded to oxygen once, oxygen twice, oxygen 3 times. Happens to be exactly the same here. Oxygen once, oxygen twice, oxygen 3 times. Once so they're tied after all of that, then we move over to the next atom, which is carbon, in this case for A, or proton for C. So carbon's got a higher atomic number than proton, so it should be A would be third and C would be fourth. So that's good, excellent. Let's try the next one, unless there's any questions. Oh, okay, well, let's try the next one. Similar sort of question here. Determine the priorities of each of these 4 substituents. Super. Okay, let's see how everybody did. Responses. C number 1. A, B number 2. D, and then A. Okay, so that is correct. So let's see here. Oxygen's atomic number is 8, so C beats out all of the 3 carbons. Then if we look at the carbons, this carbon here is bonded to carbon once, carbon twice, hydrogen. So CCH. This carbon is bonded to oxygen, oxygen proton, so that's OOH. And this carbon is bonded to carbon once, carbon twice, oxygen. So this would be OCC if we're ranking them in order. So B, because it's bonded to an oxygen, then another oxygen, beats D, which is only bonded to one oxygen. So B would be second. Oxygen beats carbon, so D would be third. And substituent A would be fourth. Good. Okay, let's move on to putting this all together. So in each of these molecules, in A, B, and C, there's a chiral center, namely here, here, and here. Now what you need to do is assign an R or S configuration at each center. Remember, you want to have the lowest, the 4th place priority group pointing away from you to do the clockwise versus counterclockwise test. Okay, so let's look at let's see what everyone put. Responses. S, R, and R. And there's most consensus around the second one, this one. Okay, so let's see here. So in molecule A, the highest priority, if we're looking at carbon here, nitrogen, nitrogen beats carbon. So what's number 1? This carbon is bonded to a carbon and 2 hydrogens. This carbon is just bonded to 3 hydrogens. So that means this is 2 and this is 3. So this is a right-hand turn, which is R. But because the proton, the lowest priority substituent is pointing towards us, that's the wrong perspective. We've got to reverse this answer. So this becomes S. So this should be S. In molecule B, so the chiral center is here. So we've got a methyl group. So that means that it's only bonded to 3 hydrogens. This carbon here is bonded to oxygen, oxygen, carbon. So 2 oxygen twice in this carbon over here. And this carbon here is bonded to a carbon and 2 hydrogens. So the highest priority would be the ketone, then the ring carbon, and then the methyl group would be last. So this is a counterclockwise turn. The proton is pointing away, which is correct. So this is S. And then carbon, and the third molecule here, the carbon's going to be 3 because it's lower than the 2 oxygens. This oxygen is bonded to a carbon. This oxygen is bonded to a hydrogen. So this would be 1, this would be 2. And This is a right-hand turn, so that's R, and the proton's pointing away, which is what we should have. So it should be SSR if everything is correct here.
There was only one S option.
Oh, was there? Well, that's bad. Well then, that's not good. So we will have to correct we will have to correct that next time then. Okay, so let me get rid of this stuff here. Okay, let's try the next one. Now, I remember I did put enough R and S options on this one, so we shouldn't run into the same problem. So here's a molecule with 3 chiral centers. What is the configuration at each? I have to edit that question. Okay, let's see how everyone did. Responses, SSSS. And most confident about number D, about number C. Okay, so let's go through these one at a time. I am trying to draw. Nitrogen, number 1 for this carbon here. Carbon up here is oxygen, oxygen, carbon, 1, 2, 3. Carbon here is fluorine, carbon, hydrogen. Fluorine is better than oxygen because higher atomic number, 2, 3. So this is a right-hand turn, R, but the proton's pointing towards us, which is wrong, so that's got to become S. So A should be S. On carbon 2, fluorine will be number 1. Let's erase this. This carbon is bonded to nitrogen, carbon, hydrogen, and this carbon here is bonded to carbon, hydrogen, hydrogen. So this would be 2, this would be 3. The proton is pointing away, so that's the correct perspective. So this is a counterclockwise turn, which means that this is S. And in the third case, this carbon is bonded to carbon, carbon, hydrogen. This carbon is bonded to carbon, hydrogen, hydrogen. And this one's oxygen, oxygen, carbon. So this will be number 1. This is number 2. This is number 3. And again, the proton's pointing away, which makes our life easier. So this is a counterclockwise turn. So this is also S. So the correct response is, let's stop this, is SSSS. That is correct. Let's erase some of this stuff here. So let's see here. Let's erase this. God help me. Clear all drawings. Okay, good. Okay, so that was basically, I think that was the last of the questions here. Let us go on to the next thing. Right, so the last bit of stuff that we had to do in this section was look at compounds that have more than one chiral center. So threonine is an example of this, where there are essentially two chiral centers here on this carbon and on this carbon, because each carbon's got 4 different substituents. In the case of this carbon here, we've got a carboxylic acid, an amine, the rest of the molecule, plus a proton. This carbon, a methyl group, hydroxyl group, and the rest of the molecule plus the proton. So we've got 2 chiral centers, and whenever you've got multiple chiral centers, there's a little formula that you can use to determine the number of stereoisomers there's going to be, which is basically 2 to the n. So if we've got 2 here, 2 squared is 4. And we've basically drawn all 4 of them here. So if we've got 2 wedges coming towards us, then the enantiomer of this compound is going to have all of the chiral centers reversed. So the 2 dashed lines going back. There's also a stereoisomer in which, say, one of them, the hydroxyl group's pointing towards us and the amine's pointing away. And there's the exact opposite of this, where the hydroxyl group's pointing away and the amine's pointing towards us. So these are basically the 4 stereoisomers of threonine. So, right, an enantiomer, all of the chiral centers will be reversed. So this compound's enantiomer is going to be this one, because the 2 chiral centers are reversed. This compound's enantiomer is going to be this one, because these 2 centers are reversed. What's pointing forward is now pointing away. What's pointing away is now being pointed forward. So we can go through and basically do assign a configuration at each carbon here. And if you're ever tasked with doing this and you've got 4 different stereoisomers that are here, the easiest way to do it is to choose the one which has got the protons pointing away in each case. So this first one we've drawn, the lowest priority item, the proton, is pointing away and pointing away. So if you do this, if you assign the configuration at this, for this stereoisomer, then you can basically use are there any different, okay, there's a question here in private chat, which was basically, is there any difference in the fact that these wedges aren't shaded? No, I just forgot to shade them when I was drawing this. So a wedge is, this is still a wedge, same as that. So this wedge pointing towards is the same as that. This wedge pointing towards is the same as that. I'll have to go in and change that. There was another question about internet connectivity being poor. I'll post this afterwards anyway. So if I just assign a configuration at this if I had to assign a configuration, I would use this stereoisomer because it's got the correct perspective of the hydrogens here. So this is what I've done in this slide. So this little orange star, okay, so we got our amine, that's number 1 because nitrogen's more than carbon. This carbon's number 2 because the carbon's bonded to 3 oxygens, and this carbon's only bonded to 1. So 1, 2, 3. This will be a left-hand turn, so this is S. So this orange starred carbon is S. And conversely, the carbon here, oxygen's number 1, highest atomic number. Then it's a carbon versus a carbon. This carbon's bonded to a nitrogen. This carbon's only bonded to hydrogen, so this is number 2. 1, 2, 3. This is a right-handed turn, so this is R. So this one's S, this one's R. Once we've done that, we can basically look at all of the other ones, and so if we determine that the wedge for the OH is R, that means that this pointing away has to be S. Well, here's a wedge. This one's R, it's exactly the same. This one would be S. If the wedge for the nitrogen was S, the reverse one has to be R. And then, well, this is reversed, so this is R. And then this is the wedge, this is S. So by assigning it here, I can just look at the stereocenters at all the other remaining ones and just, if it's opposite, put the S, like just reverse them, right? So it's easier to assign a configuration for the chiral centers when the perspective is correct, right? So that's how I would tackle this problem. So you'll notice that in this case here, for the enantiomers, the chiral centers are always reversed. So R becomes S, S becomes R. R becomes S, S becomes R. So this is a group of enantiomers, this is a group of enantiomers. So the chiral centers, all of them have to be exactly opposite to be a mirror image, non-superimposable. But this doesn't tell us what the relationship is between, say, this stereoisomer and this stereoisomer, or the relationship between this and this, because they're not mirror images of one another and they're not superimposable. The chiral center here is exactly the same. The chiral center here, and this one is the same, but this one's reversed, right? So there's a special type of stereoisomer in which one chiral center is the same and one or more is different. Or so for enantiomers, the caveat is all of the stereocenters have to be opposite. With this other type of stereoisomerism, one or more can be different and one or more can be the same, depending upon how many chiral centers you happen to have. And so the relationship which we just talked about, stereoisomers that are not enantiomers are basically called diastereomers. So diastereomers have the opposite configurations at some chiral centers, but the same configuration at others. So with an enantiomer, it has to be opposite at all of them. Right, so that's basically stereoisomers that are not enantiomers are called diastereomers. So now we've got, basically two different cases of enantiomers, diastereomers. There's one more trick here, and that is, let's move this down here. Here's another example, which is different than the threonine. So in the threonine version, we had a carboxylic acid on one end, and over here was a methyl group. Plus we had an amine here, which is different. But in this example, tartaric acid, we've got a carboxylic acid on each end, and then hydroxyl groups on the two carbons. So in this case, there's actually only 3 stereoisomers. So the little formula we had which was 2n. This is the maximum number of stereoisomers that's possible. Sometimes you have less, and this is an example of such a thing. So tartaric acid's got 3 different stereoisomers. The 2 enantiomers. So we basically signed a priority system here. Oxygen's 1, carboxylic acid's 2, this carbon's 3. So this is a right-handed turn, R. Hydroxyl groups, then carboxylic acid, then the rest of the molecule, again, right-handed turn. So RR, this will be SS, and then these 2 stereoisomers are identical. And this is going to be fun when we figure out, well, why this happens to be. So this is one of the basic, this is where you can have a chiral center, but a molecule is basically achiral because of a plane of symmetry. So remember, to be chiral, you can't have a plane of symmetry. And these versions of tartaric acid actually do have a plane of symmetry. The one way to depict this is to fix a little point here, and then if you pull this carbon all the way around to here, it ends up right up here. And this carbon is going to get pulled around to here. And the group, the S, which was pointing away, is going to move to here. And this carbon is going to move to here. And you end up with this, which is exactly the same as the molecule we had over here. So this sort of pivot point, you can see that it's actually exactly the same molecule. But if you don't believe me, for like, where's the plane of symmetry in this molecule, right? There's a nice way that we can draw this. We can do this. Let's take a look at that for a second. Let's clear all this stuff for a second. Let's use a drawboard here. No, what I'll do is I'll share a different screen, I think. Oh no, here we go. Right. So this was our molecule. Let's draw a Newman projection of this, because it might not be obvious where this plane of symmetry is. So let's look down this bond here. So on our front carbon, the group which is pointing, if this is our eyeball and this is our eyelashes here, so the eyelash side's up, the other side's down, right? So the group which is pointing straight down is our carboxylic acid. And we've got a left and right-handed side. So if we're looking at this from this perspective, the wedge is on our left-hand side. Because if we turn to look at the molecule, our hand, which would be pointing out of the board, is on the left. So we've got an OH here, and we've got a proton on the right. Now, on the back carbon, over here, back carbon, there's a group pointing straight up, right? And that's the carboxylic acid. The dashed line is on the right-hand side because it's into the board. So this will be on the right, OH. And the proton, which isn't drawn, will be on the left-hand side. So that's our Newman projection from this perspective. Now, where's the plane of symmetry? We still don't see the plane of symmetry. To get that, what we're going to do is we are going to rotate this 180 degrees. So going from being a staggered configuration to an eclipsing configuration. So I'm going to keep the back carbon in place, and I'm going to rotate the first carbon, the front carbon. So let's draw this. Let's get some blue. Back carbon. CO2H, OH, H. Now the front carbon I'll draw in red. So the carboxylic acid is going to rotate 180 degrees, so it's going to be eclipsing the other carboxylic acid. The hydroxyl group here is going to go 180 degrees, so it's going to go over here. So let's draw that. OH. And last but not least, our little proton, which is right here. It's going to go 180 degrees to right there. So if we want to convert this back to a wedge diagram, instead of being a zigzag, it's now bent because we have to rotate this 180 degrees. So what we've got is we've got our CO2 here, our CO2 here. The back carbon is staying the same, so the OH is still pointing away. And our front carbon's now pointing away. And the plane of symmetry, the internal plane of symmetry is right down the middle, right through here. So carboxylic acid reflects carboxylic acid, proton reflects proton, OH reflects OH, front carbon reflects back carbon. And so we've got this internal plane of symmetry like this. So drawn in a perspective like this in the zigzag, it's not evident where the plane of symmetry happens to be, but it's right down the middle when you just rotate it 180 degrees. So OHs reflect one another, carbons reflect one another, carboxylic acids reflect one another, and the two protons that are on these two carbons here, they reflect one another as well, but they're just not drawn. So we can use a Newman projection to actually to see where the internal plane of symmetry happens to be. Okay, any questions on that? Let's go back to our other screen. Right, so drawing a Newman projection is one way to see that there's an internal plane of symmetry for these two compounds here. And you could have started with either one, you could have drawn either one, and you would still, if you did the rotation 180 degrees, there would be no plane of symmetry. If we want to, if we draw the enantiomer and do a similar Newman projection sort of analysis, there will be no internal plane of symmetry. We could do that just for the sake of it. Come on, little thing. So for for one of the enantiomers, let's just use this one. If we do a similar analysis looking down this carbon here, so the front carbon, we'll draw the back carbon in blue again. The back carbon has got a carboxylic acid pointing up. The wedge is our left hand, so the wedge is on our left hand side. Proton, which isn't drawn, will be on the right. On the front carbon, pointing straight down, is the carboxylic acid. A wedge for the hydroxyl group, so that's on our left hand side. H is right here. And you'll notice that both hydroxyl groups are pointing towards us, but there is no mirror here yet. So if we want to have a mirror, these two things have to reflect one another, so they have to be eclipsing, right? So if we were to rotate this, we don't actually have to rotate it much. If we were just to rotate this so this OH is eclipsing the other OH, what we get is the following. So I'll leave the back carbon the same. O2H, H, OH. So the front carbon, this hydroxyl group is now eclipsing it. This carboxylic acid is only moving over to here, and this hydrogen's moving to here. So what we end up having is the hydrogen's eclipsing the CO2 and the carboxylic acid's eclipsing the hydrogen. So there is no internal plane of symmetry. So this guy is chiral. Any questions on that? Oh, that's net. What is the degree of rotation? So in this case here, we only rotated it, whatever this is, we only rotated the 60 degrees here to get from here to here. In the other case, we rotated it. I don't think it's really important actually for each one of these things. You want, if there's going to be an internal plane of symmetry, the groups have to be eclipsed, number one, and they have to be, they basically have to be eclipsed. So you'd have to rotate this however much it is to eclipse the other group. But you have to keep the groups in the proper perspective. So if the carboxylic acid's here and it rotates this H, where's my little laser? So you want the groups to be eclipsing to test if there's an internal plane of symmetry. So I have to rotate this carboxylic acid 180 degrees to get to here. So this has to go 180 degrees, this has to go in under 180 degrees, and they have to be in the same, so carboxylic acid, hydrogen. And then hydroxyl group, carboxylic acid, hydrogen, then hydroxyl group. Got to keep that the same. So in the previous case here, to get this to eclipse, I just rotated it a little bit. So it really just depends on what the spatial arrangement is to actually, for how much you have to rotate it. But for an internal plane of symmetry, the Newman projection has to be staggered. It has to be eclipsing. That's the key point. And all three of the groups should be exactly the same. So this is basically just saying it's hard. Sometimes it's hard to realize that there's an internal plane of symmetry here, so it's better to draw a Newman projection. And the special name for these types of compounds, this is the key point, molecules that have chiral centers but are achiral because of a plane of symmetry are called meso compounds. So tartaric acid is one example. One of the stereoisomers is has an internal plane of symmetry and is achiral. So if you put that in a polarimeter, there will be no rotation of the plane polarized light. The other two stereoisomers will each, because they will each rotate plane polarized light the exact opposite directions by the same magnitude, because they are enantiomers. Okay, so here's basically a final little review on these types of things. Where's my laser? So, enantiomers. The physical properties of enantiomers, they are the same except for optical rotation and solubilities in chiral solvent. So if it's an achiral solvent, they'll have the same solubilities. Chemical properties are the same, except if they're reacting with other chiral molecules. So there's a whole bunch of possible answers to this. So just keep that in mind. So, but if it's an achiral, the chemical reactivity will be exactly the same. Biologically, they are completely different because most of the biomolecules that are important are all chiral. So they got a big difference for biological activity. Now, diastereomers and meso compounds, they can have different physical, chemical, and biological properties. Because, yeah, so they're a mixed bag of all of those things can be different. And this is useful in a number of different ways. All right, so let's go to the last little bit here. So last class I talked about sometimes you can, if you're looking at the chemicals you're using in your lab or what it might be, sometimes you'll see a plus minus whatever your compound has to be. So in this case, lactic acid. Whenever you've got a 50% of your mixture is each of the two enantiomers, we call this a racemic mixture or a racemate. And so these will have an optical rotation of 0 because whatever this enantiomer rotates the light, this one will rotate it exactly the opposite. So often in the course of doing some reactions, you can make both enantiomers in a given reaction. There's been an awful lot of work done over the years of selectively making one enantiomer and not the other. And reactions which this happens are what we call enantioselective reactions. And there's all sorts of research being done on that. But back in the day, when you had a racemic mixture, you wanted to be able to separate these two compounds out from one another. And we're going to use basically the principles from the previous slide to be able to do this. So the physical properties they're basically the same, but their solubilities in chiral solvents was different, like that. So you could try to separate them using a chiral solvent, but there aren't a whole lot of chiral solvents. What we're going to do is we're going to use the fact that diastereomers have different physical, chemical, and biological properties. And the way that this works is kind of neat. So this is what we call a resolution, chiral resolution. So if you've got two enantiomers, so the two enantiomers of lactic acid, you can react them with a chiral amine. So this reaction is purely just an acid-base protonation, deprotonation reaction. And so the nitrogen here is going to remove a proton from the carboxylic acid, and it's going to form two salts, right? So we got an anion and a cation. They're going to clump together to form a salt. And the other, if this amine deprotonated this would be the other salt that you would form. Now, the interesting thing about these two salts is that this salt here has got an R group and an R. This salt here has got an S and an R. And so with diastereomers, the melting point, the solubilities, all of these things are different or can be different. So you've taken two enantiomers, you've reacted it with a amine, which is one, so, and then you've generated two diastereomers out of it. And so the physical properties of these two salts will be different. One of these might be more soluble in water, one of them might be, or some other solvent, one of them might be insoluble. And so you can separate the two out based upon their solubilities because they'll have different physical properties. Then you can recrystallize them and basically, and if you want to get your original thing back, so if you separate these two out, you want to get your original thing back, all you need to do is protonate it, right? Then this carboxylic acid becomes protonated and you've got your S version of lactic acid or your R version, because you can separate these two salts out. And in fact, that's what Louis Pasteur did way back, like all those years ago. He had tartaric acid and he was looking at it through the salts of tartaric acid, and he was looking at it through a microscope, and he noticed that some of the little crystals, they were mirror images of one another. So he basically separated these two things out, the two salts out with pliers, and when he dissolved them, they would rotate the plane polarized light in opposite directions. So it's kind of neat that that's exactly what how that worked way back in the day. All right, so that's basically, this is basically a chiral resolution. So, and you might say to yourself, well, how did you get this amine to be chiral and only one of them? There are lots of chiral amines in nature. The alkaloids are basically chiral and they're bases. So there's plenty of chiral bases in nature that you can use to perform this type of resolution. All right, so any questions on that? Okay, let's go on then. So here's basically the review of isomers. So the first departure point is they've got the same formula and different connectivity. So these would be constitutional isomers. Ethanol versus dimethyl ether, those would be constitutional isomers. Stereoisomers, they have the same connectivity but different geometry. If they are mirror images and non-superimposable, they would be enantiomers. If they are not mirror images and not superimposable, they would be diastereomers. And then you can have basically configurational diastereomers, which is what we just done, or cis and trans diastereomers. So with double bonds, methyl groups being on the same side, cis, or being on opposite sides of the double bond, trans. Or the first place where we came across this was with ring systems, because there's no free rotation. Are the two methyl groups on the same side, or are they on opposite sides? So these would be cis and trans. I guess I got too close to the edge. Trans. Two methyl groups are across the ring. So that's basically, oops, that's basically all of the various types of stereo isomers here. Okay, good. Okay, so what we needed to do next was basically talk about a review of organic reactions. So we're going to talk a bit about like basically the classifications of different types of reactions, and then how to draw them, how a reaction takes place and that type of stuff. So in general, what we do is we look at what occurs and try to learn how it happens. And physical chemists are wonderful at doing this, and there's a whole subfield of organic chemistry, physical organic chemistry, which talks about mechanisms and that type of stuff. So, but there are four general types of reactions that we're going to talk about here. The first is what we call addition reactions. So two reactants add together to form a single product. So this is 1 + 1 = 1. So an example would be ethylene, where you've got a double bond here, hydrogen bromide. And so the hydrogen gets added to one carbon, the bromine gets added to the other carbon, and then you've got something, product like this, bromoethane. So we're going to see in the next, later on, just how this addition takes place for putting a carbon, for adding a hydrogen here and a bromine there. So that's the first class of reactions, 1 + 1 = 1, so addition reactions. The second class is exactly the opposite. So you've got your bromoethane here, and then with the use of a base, you break it apart, so you've got your alkene plus your HBr. So this is basically the opposite. One molecule splits into two molecules. There is a, in this case, it needs some help with the base. So in the addition reaction case, if we're talking about order and disorder, we're going from 1 + 1 = 1. So the disorder in this reaction is actually decreasing, right? Because we're going from 2 to make 1. And here, we're starting with 1 and we're making 2. So this elimination reaction is increasing the disorder in the system. That becomes important a bit later on. But so addition reactions and elimination reactions, exactly the opposite. Then there is substitution reactions. So we're going to exchange parts between two components. So we're replacing a chlorine with the iodine to make iodomethane and sodium chloride in this case. So in Gen Chem, these might have been called double displacement reactions. So we're going to substitute one substituent for another. So substitution reactions are really important. We'll talk about this at length towards the end of the class. Another classification is rearrangements. So this is just a reorganization of the atoms and bonds to give a stereoisomer. So these are often catalyzed by acids. And so you've got 1, 2, 3, 4 carbons, so a butene, and the presence of some acid, this forms the 2-butene, but more specifically, the trans-2-butene. So this would be, what types of isomers are these? These would be the constitutional isomers, because they are not, they've got the same atoms, but in this case, the double bonds between carbon 1 and 2, this case, the double bonds between 2 and 3. So they don't have the they've got the same formula, but they've got a slightly different connectivity there. So those are largely the four main class of reactions that we're dealing with. So, reaction mechanisms. So, a mechanism describes in detail exactly what takes place at each step or stage of the transformation. So, yeah, this is drawing mechanisms can sometimes be a challenge, but the nice part is that when you do that, I get a question. Question is about, is the disorder increasing or decreasing in substitution reactions? In this case, it's basically the same, right? So you've got two components and it's going to two components. So there's, it's basically staying the same in that case there. Okay, so mechanisms describe the detail exactly what takes place in each stage of the transformation. So in a lot of the things we're doing, the reaction takes place over, sometimes it's just one step, sometimes it's a series of discrete steps, like 2, 3, 4, whatever it happens to be. And so in each step of the mechanism, we are either going to break or form covalent bonds. So like if you think about, let's think about a nice little, let's draw something here. So this acid-base reaction, right? Let's do an analysis. So we have got, remember our old rule, negative goes to positive, or delta negative goes to delta positive, or negative goes to delta positive. It's always negative charge, the electrons are going to be attacking the partial positive, positive, whatever it happens to be charged. So, and we actually were doing some mechanisms during the acid-base section, right? So this bond is polarized in this direction. The proton's got the delta plus. On the edge of the screen, it doesn't draw. The oxygen's got the delta minus. We've got our negative electrons, and they're going to grab that proton, and then these electrons are going to move over to that oxygen. So our products are going to be water, and then the deprotonated carboxylic acid. And so we're basically, this is the mechanism of how this works. This grabs this, that departs. So what type of, this little, like if we wanted to classify this acid and base reaction, we're basically, this is all just a transfer of proton sort of, I guess you could put acid base is a fifth class of reaction. It's just a proton transfer, right? So, but you are technically changing the substituents on this. It's not elimination. It's not a addition reaction where changing the place where this hydrogen's bonded to. It's going from here to there, right? So this would be, technically, it would be a, if we had to use one of those four, it would be a substitution reaction. But what we're substituting is just, is a proton. So this is basically a mechanism, and but in this case, it's in one discrete step. You're forming a bond between oxygen and hydrogen. You're breaking a bond between hydrogen and oxygen. And you're doing this because hydrogen can only be bonded to one thing at any time. So if these electrons are going to make a bond here, these ones have to be breaking to go onto the oxygen. So the steps in the mechanism are going to involve either formation of bonds or breaking of bonds. And these bond breaking and bond making steps can either occur individually or in combination with other steps. So in this case, this is a combination thing. So this bond's being made as this bond's being broken. But there's other instances where a bond can break first, and then a bond will form in the second step, which would be a discrete step. When several bond making breaking steps occur at the same time, there's a special name for this, and to say this is a concerted reaction. So there's some really good examples of that, which we'll get to in a second. So I'm just checking okay, got lots of time. So remember, there was a variety of ways in which we could depict stuff. At the start of the review of this class, we talked about, at the start of the term, I guess, we talked about the ways that the movement of electrons, if it's one electron or two electrons. And for most of the class, like polar reactions versus radical reactions, we don't really talk about these sort of homolytic bond-breaking processes, but there's a whole class of reactions in which all of the electrons that are moving are just one. So in this case, A and B, if this bond breaks, A is going to have one electron, B is going to have one electron. So this is a radical process. So it's the movement of one electron. So if we wanted to show this homolytic bond breaking, each one of these, this bond is each going to get a fish hook arrow going to each fragment to give these B with an electron, A with an electron. There's also the heterolytic bond breaking. So this is what occurs in polar reactions, where these electrons are going to move to the more electronegative atom, and the other one's going to have a positive charge. So we've got an extra electron here, so it's going to have a negative charge. We're missing an electron, so A is going to have a positive charge. So you get charged species in heterolytic bond breaking. I think I just answered the question here below. The more electronegative atom is going to get the negative charge if we're doing it correctly. Now, if we want to form bonds, it's exactly the same thing, but opposite direction. So two radicals can come together to form a bond. This would be a homolytic bond forming, so a radical process, or there's a hetero version of this where two electrons are going to go to form a bond. So this would again be a polar reaction. You've got charged species and they get together to form a neutral species. The key point here when we're talking about polar reactions is that, so the movement of two electrons, it's got the pointy arrow. The tail of the pointy arrow is where the electrons are. So in this case, these lone pair electrons. So that's where they start, and the pointy end goes to where the electrons, or it's ending. So negative goes to positive. So the pointy end is always going to be pointing at positive charge, partial positive charge, polar bond to something. So that's where they're going. So the arrow is where the electrons are going. a common mistake is if we were doing that exact same reaction we did before, and we're going to make water. A common mistake which is done is often this. Let me draw the negative charge on. Well, this H ends up on this oxygen, so it's going here. But the tail of the has to be where the electrons are. This proton has no electrons, so the tail is always where the electron lone pairs are, and it's going to point to the positive charge. So the pointy end is pointing towards the positive or the partial positive, and the tail is where the electrons are, the negative or the electrons, because electrons are negative. So let's put a little red X through this arrow. Oops. Let's put a red X. Certain things which get the big red X are arrows like this and 5 bonds to carbon, right? That's not good. So there you go. Okay, then there's one other class of compounds, pericyclic reactions. We could do an entire course just on pericyclic reactions. In fact, you do a section of advanced organic on pericyclic reactions. This is, again, this would be a concerted reaction, concerted. In this class of reaction, there really is no negative to positive type thing. All these bonds are being broken and at the same time. So they're all being formed at the same time. So this is a really special class of reactions called a cycloaddition. And the little numbers here talk about the pi electrons. So you've got 1, 2, 3, 4 pi electrons. You've got 1, 2 pi electrons, so 4 plus 2. And you make sigma bonds and a new pi bond. This reaction is the Diels-Alder. You'll do the lab of this, I think, next term. And you're making 2 new sigma bonds. Remember, sigma bonds, it's a head-to-head overlap of orbitals. So they're stronger than a pi bond, which is a sideways overlap of orbitals. So this reaction, this works great. The people which discovered it won the Nobel Prize for it. And this is 1, 2 components to 1. So this is it's an addition reaction. And you're making a cycle, so it's a cycloaddition. So this is another one which is entropically isn't particularly favored, but it still works because of enthalpy. So this last little bit here is most of the stuff we're going to be doing is polar reactions. So this is why the old mantra exists, negative to positive. But we will look at a couple of the pericyclic reactions, and we do some of this stuff in the lab. And I think we won't be doing a radical reaction this coming year because of COVID, which is a bit of a shame. But a lot of the useful radical reactions make polymers. So one of the things that we used to do is make polystyrene and this sort of stuff in the lab, but not this year, unfortunately. Right, so radical reactions, they're important in industry, lots of biology. And radicals are reactive because they usually only have 7 valence electrons. So that odd number, they want their octet filled. So this is often, they're quite reactive. I think what we're going to do next is talk a little bit about radical reactions. So they can undergo substitution reactions just like polar compounds can. So R is just any unpaired radical or starting product. And when it does a substitution reaction, so we're going to form a bond between R and A, and then one of the electrons is going to go off to B. And so then this radical is going to carry on with other reactions. This is what makes radical reactions. They're often called chain reactions because they are self-propagating. You can also have an addition reaction. So same radical, it's going to add to the double bond. So you're making a bond between radical and carbon, which is what we've just done here. And now these electrons are moving on to the carbon. So now we've got a radical here, and it can react. This should actually have a should be a fishhook. Right. So there's three basically defined steps when it comes to radical reactions. So the first one is you need to generate a radical, which we call the initiation step. Then there's propagation steps. So this is the chain reaction. So this is the chain reaction. And the propagation steps, there can be, depending upon the reaction itself, there can be 1, 2, or 3, maybe more. And last but not least, we need to stop this thing, the termination step. And this is typically when two radicals combine. That's basically a termination step. So one of the one of the useful reactions that we've got, which we can use. Remember, our friends, the alkanes, they were pretty much non-reactive to most species. There was two basic exceptions. The first was you can burn them in oxygen, like you can do a combustion reaction like we do in our cars. The second is radical reactions. Using UV light. So this is what this HV means, is basically we're initiating this reaction with light. And the radical reactions typically involve the halogens. Cl2, Br2, or a safer version of Br2 that we can use. Chlorine radicals are super reactive. So it's typically bromine, which is more, how shall I say, useful because there's a bit more selectivity with the bromine reaction than with the chlorine reaction. And I'll get into that in a second. But this is basically a substitution reaction. What we're doing is we're replacing one of the H's with the chlorine and the chlorine with an H. So we're basically exchanging parts here. And so this is where we'll basically start next class. So this is a substitution reaction using doing some radical chemistry. And you need UV light, and all of the bonds are going to involve fishhook arrows. And the last part is that our mantra doesn't work here, like the negative, the delta negative going to delta positive. That doesn't work with radical reactions because there's no charges. So there's going to be basically no charges when we're doing the mechanism of how this works. But the octet rule has to be followed. So we're going to see that if we're breaking bonds and making bonds, we don't want to have carbon with more than 8 valence electrons. We don't want chlorine with more than 8. They can have less. So being a radical, but they can't have more. So in all of these processes, we are going to make sure the octet rule is at least never exceeded. It can have less, but not more. And I guess the other final bit is that we can actually use the bond strengths to predict how this is going to work, because we're going to be breaking the weak bonds and forming stronger bonds. So we'll look at this particular reaction next class. So and then we won't see radical reactions for a little while until organic 2. But it is synthetically useful at the start of a synthesis. So we're going to use that quite a bit in organic 2 when the time comes. But anyway, this is where we're going to start on Thursday. Chlorine's this is very reactive. I remember when I was your age, one of the guys, our teacher, came into the class with this bottle of basically encased in aluminum foil with a cork on it. And then when he ripped open the aluminum foil and the light hit what was inside the thing, basically the cork blew off the top of the flask. And it was basically a reaction very similar to this. It was a radical reaction. It was producing gas, and it made the whole thing go, the cork fly off the top of it. Anyway, that was a fun class. Maybe I'll dig up that reaction on YouTube somewhere, and I can show it to you. But anyway, any questions? All right, well, I'll see everybody on Thursday. All right.